Welcome to the Deep Dive, where we crack open complex subjects, extract the golden nuggets of wisdom, and make them genuinely useful for you. Today, we're embarking on a journey many of you are either on right now or maybe gearing up for: calculus. It's a subject that can sometimes feel like trying to build a castle with individual grains of sand, right? But what if you could learn how to mold those grains into solid, unbreakable bricks?
Absolutely. And as someone who recently navigated that very journey, I can tell you it's often less about raw intelligence and, more about smart learning strategies. We're not just reviewing math today, we're diving into how you can learn it more effectively. We'll explore some foundational calculus I concepts, not just as facts, but through the special lens of learning science, especially the power of chunking knowledge into your memory. This deep dive is really all about giving you a shortcut to being well-informed and hopefully well-prepared.
All right, we're going to unpack some key ideas from our calculus source material, but also drawing heavily from Barbara Oakley's insights in A Mind for Numbers. Think of it maybe as a chance to refresh those foundational mathematical chunks you might already have and learn how to build new ones even stronger so they really stick. The core idea we want you to walk away with is that less focused study, if it's strategically interrupted, can actually lead to deeper and more lasting learning. We'll show you why your brain's diffuse mode is kind of your secret weapon.
It's truly about working smarter, not just harder in your calculus journey. And honestly, I wish I'd known some of these techniques much earlier.
Okay, so let's start building our mental toolkit for calculus. One of the most fundamental skills, maybe often underestimated, is truly mastering inequalities. For someone who's maybe a bit rusty, what exactly are we talking about here, and why are they so crucial in calculus?
Great question. At its simplest, inequalities are mathematical statements that compare two expressions. They tell us if one is greater than, less than, or maybe equal to another. Think of them as defining boundaries, like by 5 or 3 arrow plus 1. But the key insight isn't just knowing the rules for moving them around, manipulating them. It's recognizing that inequalities aren't just about comparison. They're about defining regions or constraints.
Okay. Regions or constraints, not just bigger than.
Exactly. And this foundational chunk is crucial because calculus is often about what happens at and around those boundaries, things like limits or continuity.
That's a really helpful distinction. Boundaries, not just comparisons.
Yeah.
So when you're learning these, what does chunking actually look like for inequality rules? How do you do it?
Well, instead of trying to memorize isolated rules, like, if you multiply by a negative, flip the sign, you want to chunk the entire behavior of inequalities. Our foundational texts mention properties like the transitive property. If A is less than or equal to B and B is less than or equal to C, then A must be less than or equal to C. For me, I'd practice a few problems. Then maybe step back and ask myself, okay, what are the core principles here? I'd group them mentally. These are the rules for adding, subtracting, these are for multiplying, dividing, and this is about how they combine. So when you think inequalities, your brain should instantly recall this whole suite of comparison behaviors as, like, a single unit.
Okay, so it turns multiple steps into one manageable thought. That frees up your working memory for the harder stuff, right?
Exactly. It's about freeing up that mental bandwidth. Chunking isn't just grouping, it's forming meaningful relationships between the pieces of information, like building a mental scaffold.
A scaffold.
Yeah, I like that.
Okay, so with those algebraic chunks in mind, let's look at exponential laws. These are the rules for how exponents behave. They can seem simple, maybe, but they underpin so much of calculus growth models, the definition of E. Why do these often get poorly chunked?
Yeah, I think it's because students often just see them as equations to memorize, like ax plus y equals x, but these aren't just equations, they're patterns for how exponents behave. To chunk these effectively, you need to see the pattern in action. Don't just write them down over and over. Practice problems where you actually apply them, see that ax-a pattern, and immediately know it's ax plus y without having to consciously recall the rule itself. I found it helpful to really think about the meaning, exponents as repeated multiplication. Then the rules felt less arbitrary. This repetition and recognition binds these operations into a single accessible chunk. It's like converting a big file into a .zip file.
That .zip file analogy really works. Okay, so from these algebraic relationships, let's bridge over to geometry with the distance formula. This classic sometimes feels a bit abstract until you actually visualize it. How would you chunk this one?
This is a perfect example of chunking geometric and algebraic connections together. The formula, dpq, squart, by 1, 2, plus y1, 2, it's not just a string of symbols to memorize. The real chunk here is its fundamental link to the Pythagorean theorem. You should almost instantly visualize forming a right triangle on the xy plane.
Right, with the distance being the hypotenuse.
Exactly. The distance you want is the hypotenuse, and those by 2 u by 1 and y1 terms, they're just the lengths of the other two sides, the legs of that triangle. When you understand that visual and algebraic connection as one single concept, that's when you've chunked it. You're not just recalling a formula, you're recalling the geometric principle behind it. Makes it much harder to forget.
I see. It's not just the formula, but the sort of story behind the formula that really clicks. Now, let's zoom out a bit to the fundamental shapes that underpin pretty much all functions, the parent functions. If you can chunk these, you're not just memorizing equations, you're instantly recalling their entire personality, right?
Exactly right. When you learn about functions like, say, fx by 2, the parabola, or fxx, the v-shape, or fx score tx, the hook shape, you're not just learning an equation. The chunk for a parent function really includes its shape, its domain where it's defined, and its range, the outputs all bundled together. Imagine quickly sketching the graph in your mind. That visual chunk lets you anticipate its behavior, how it might transform, without needing to plot points every single time.
So you made flashcards with the sketch.
Yeah, I did. Equation on one side, quick sketch on the other. Not just the definition. That visual recall made a huge difference for me. It's a quick, intuitive reference for your brain.
That makes sense. Okay, this next concept, average rate of change. This is where many people get their first real taste of calculus ideas, isn't it? Things start getting interesting here.
Definitely. This is where we build a really crucial bridge from algebra to calculus. The average rate of change is, well, essentially the slope of a line connecting 2 points on a curve. Just like you learned in algebra with y=x plus b, for a straight line, that rate of change, the slope, is constant. But for curves, like y by 2, the average rate of change depends on which 2 points you pick.
So the steepness changes depending on where you look.
Precisely. And the big conceptual chunk here is realizing that rate of change can vary, and that we start getting interested in how that rate changes at any specific point along the curve. That idea of a varying rate is what leads us straight into the concept of instantaneous rate of change, which is, the derivative. Chunking this understanding is like building a mental stepping stone.
That's a powerful connection. It's not just the formula, but understanding the implication. It's not constant anymore. Okay, finally, let's touch on real lines and intervals. These seem basic, maybe, but they're fundamental for defining domains, solutions, everything in calculus. It's where our numbers live.
Absolutely. Visualizing the real number line itself and understanding the different types of intervals, open, closed, half open, is key. You're essentially chunking the visual representation with its algebraic notation. So for instance, when you see the notation AB for an open interval, your brain should instantly picture that segment on the number line and know that A and B themselves are excluded.
Right. The parentheses mean not included.
Exactly. And with square brackets like 2, 5, you immediately see the segment where 2 and 5 are included. This connection between the symbols and the spatial picture is a really powerful chunk. If you can't visualize these basic boundaries, more complex ideas like limits or continuity become much, much harder to grasp.
Okay, we've just powered through some foundational calculus concepts, really emphasizing how to chunk them. But for our listeners, what's actually happening in our brains when we chunk information like this? I mean, we use analogies like zip files and drawing mortar, but what's the neurological process going on?
Yeah, this is where Barbara Oakley's work in A Mind for Numbers is so insightful. Our brains basically have two main modes of thinking, focused mode and diffuse mode. When you're intensely concentrating on a math problem or, listening intently to this deep dive right now, you're in focus mode. Think of it like a pinball machine where the bumpers are really close together. Your thoughts travel along precise, familiar routes, following established neural pathways.
Okay, so it's good for direct, step-by-step problem solving when you know the path.
Right. And chunks fit in because when you've practiced and really understood something like how to factor a quadratic that becomes a strong, compact neural pattern, a chunk. Now, instead of your working memory having to hold on to every single detail of factoring, it just pulls up the quadratic factoring chunk as one item. And this is vital because our working memory is surprisingly limited. It can only hold about 4 slots of information at once. Chunks dramatically ease that burden.
Like grabbing the whole .zip file instead of every individual file inside it makes your focused mode much more efficient.
Exactly. You aren't processing every character, just the file name, metaphorically speaking.
Okay, so a chunk helps us use that focus mode better. But what about when we're stuck? hitting the same bumpers over and over, not getting anywhere. A lot of students, especially when a deadline is looming, feel like they just need to push harder in that focus mode.
Right. And that's often counterproductive. That's precisely when you need the diffuse mode. In this mode, the pinball bumpers are spread far apart. It allows your thoughts to make more distant connections, bounce around more freely, and gain new insights. Being able to switch between focused and diffuse modes is absolutely crucial for learning, especially in subjects like math. You put in the hard focused work, build some initial chunks, then you step away. Go for a walk, take a nap, listen to music, do something else entirely, anything that isn't thinking about the problem.
Let your brain work on it in the background.
Exactly. Let your diffuse mode work its magic. When you come back to the problem later, those chunks you built might suddenly connect in new ways. This helps you overcome something called the Einstellung effect. That's getting stuck on one particular way of thinking, even if it's not working. True breakthroughs often happen after you stop forcing it.
That makes so much sense. It really is like letting the mortar dry between the bricks of knowledge you've laid down. I can see why stepping away is productive, but convincing a student under pressure that it's not procrastination, now it's tough.
Oh, I've totally been there. It feels wrong to step away when you're stuck and stressed. But Oakley's analogy is spot on. Trying to learn everything at once, cramming, is like building that brick wall without letting the mortar set. The connections just don't solidify properly. You might finish the wall, but it's shaky, unstable. The key is understanding that practice makes permanent, but it has to be the right kind of practice. You need varied practice, applying concepts in different situations, different types of problems, to build solid, adaptable neural patterns. And critically, spaced repetition.
Spaced repetition. Reviewing material over days or weeks, not just cramming.
Exactly. Reviewing over several days or weeks, not cramming it all in the night before. This helps solidify those memory traces, making the chunks robust and easily retrievable, even under pressure, like during an exam.
Okay, and what about those moments when we think we understand something, but we actually don't? That's a trap I think pretty much everyone falls into.
Ah, yes, the illusions of competence. This is a huge one. So many students reread their notes or textbooks repeatedly, or just look at solved examples and think, yeah, I get that. But that's far less effective than retrieval practice or self-testing. When the book is open, or the solution is right there in front of you, it feels familiar, creating the illusion that the material is actually securely in your brain.
But it's not really yours yet.
Exactly. It's not truly yours until you can recall it independently. Actively trying to recall a concept or solve a problem without looking at the solution, that's how you truly form and strengthen those chunks. It also forces you to figure out what you don't understand, and being able to articulate your confusion is like 80% of the battle.
Pinpointing the confusion.
Yeah.
Yeah, that makes sense. So close the book. Test yourself.
Close the book. It's uncomfortable, but it works.
Wow, what an insightful deep dive into learning, really. So for our listeners navigating their own calculus journey, what's your ultimate, most actionable advice for intentionally forming these powerful chunks?
Okay, I'd say it's three main things, and honestly, this applies way beyond calculus. First, deliberate practice. Don't just do problems to get the answer. Really understand why each step works. Connect it back to those core chunks we talked about. Second, self-test relentlessly. Close the book, try to write out explanations of concepts from memory, work problems without looking back. Active retrieval is key. And third, constantly try to link new knowledge to old ideas. When you encounter a new concept, consciously ask yourself, okay, how does this relate to something I already know? Like seeing the distance formula and immediately thinking Pythagoras.
The more connections, the stronger the chunk.
Exactly. The more connections you build, the stronger and more useful your chunks become. And remember, sometimes learning slowly, taking time to make those connections, actually means you learn more deeply and it lasts longer.
That's fantastic practical advice. It really is about building a more effective brain for tackling any complex topic, mastering the art of learning itself. The journey through calculus might feel daunting sometimes, but with strategies like these, you're not just solving problems, you're literally building a more capable mind. So keep practicing smart, embrace the challenge of building those mental superhighways, and you really will be amazed at what you can achieve.
Couldn't agree more. Until next time, keep exploring, keep questioning, and definitely keep chunking.